Hi everyone, my name is Nuno, and on behalf of my co-authors Emre, Fabian and Christian, I present to you Similarity-Based Interpretable Image Classification with Neural Networks. We argue that successful deployment of AI-based methods requires user trust. And we believe that this can be achieved through first understanding how the model takes its decision, that is, understanding its internal mechanisms, and additionally reveal what parts of the input data drove the decision. Previously inherently interpretable methods provided explanations that could be decomposed into three pillars. First, there are local explanations, which explain a specific decision given one test sample. However, earlier research found that these local explanations might not necessarily be faithful, meaning they don't fulfill some axioms established in the literature. Finally, we called it human intuitive here, but it could also be global explanations, which help you understand the overall decision-making of the model. For example, there's case-based reasoning as implemented by Proto-PNet and another Wachinger. However, none of the previous methods combined all three pillars, and this is where SIC comes in and fills the gap. SIC leverages the B-Cos transformation, originally proposed by Moritz-Böhler et al. It is essentially a reformulation of the linear transformation commonly found in any type of neural network, and it reformulates it as follows. So first, you normalize your weights of your layer, and additionally, you introduce a parameter b that penalizes if the input features are poorly aligned with the weights of the current layer. Reformulating it into the matrix form shows that it's essentially an input-dependent rescaling of the weights of a single layer. Because neural networks discard all nonlinearities and biases to enable summarizing the forward paths of a neural network in a single linear weight matrix. We prove in our work that the explanations extracted from this weight matrix fulfill established axioms. Second, we build on the Wachinger net, which has shown great interpretability features as it works similar to k-nearest neighbors. Its training is achieved by randomly sampling support samples for each class, for each batch from your training set, and then computing the probability of a class as a softmax between the test samples and supports. Conceptually, SIC extracts latent features using a B-Cos backbone. It takes this decision by finding representative samples of each class after training using k-means and replacing the k-means with the closest latent vector of the training sample. And for an unseen test sample, we can now compute the similarities between the support samples, or support vectors in latent space, to the latent test sample. Leveraging the algorithm of B-Cos transformation for creating explanations, we can then compute class-level explanations, and you see that they are deviating quite a lot here. On a technical level, SIC leverages the B-Cos transformation for its encoder and extracts latent features f, which are projected into positive space. Additionally, we follow the training pipeline of the Wachinger and randomly sample support samples from the training set, for which we also extract support vectors. And then we compute specifically the B-Cos similarity between a test sample or sample of interest and the support vectors, and then take the sum of these evidences of this class to do our final prediction. Importantly, we can now summarize the forward paths of this model as a single weight matrix and compute class-level explanations, as seen here on the right. We use the Pascal VOC dataset, as seen in this example, for multi-label classification, the RSNA dataset for medical image classification, the Stanford Dogs dataset for fine-grained image classification, and finally the FunnyBirds dataset to do quantitative measures of the explanations provided by SIC. As seen in this example, the explanations for different classes are deviating. At the top, you see that the model primarily used features from the bottle to predict that it's a bottle. And at the bottom, you see that the bottle didn't play any role in predicting the class dog. We can also show the explanations for each support sample by feeding the support sample into the network and then computing its explanation in terms of the support sample's activation. We do this because we want our model to use case-based reasoning as its reasoning mechanism. So we can provide you with a set of cases of the same class and show you what image features the model encoded for this class. So you can check easily if the model, given a test sample again, used similar features as it did in the prediction or in the encoding of your support samples. In this example, we used the RSNA dataset to differentiate between samples showing opacity in the lungs and samples that don't have opacity. The variability in support evidences is quite high. And evaluating the support contributions of the different support samples shows that the support sample number 3 pretty much encoded the whole input image. And this is something that's not really desired. You see that it's also sensitive to the left-right marker, and this is obviously a feature that we don't want the model to use. Evaluating the support samples of the class showing no opacity also suggests that support sample number 2 pretty much encoded the whole input image. Evaluating the latent space shows that there's a quite continuous region for the two classes and that support samples 0 and 3 are pretty close to each other there. We believe that this is due to the model not being able to differentiate between these two classes well and finding a good decision boundary. What's important here is that as a user you can now decide what you want to do as a second step. Do you want to discard the model? Do you want to retrain the model? Or what else? Now we also evaluated the T/S/N/E embeddings on Pascal VOC, and we find that the clusters of different classes are quite homogeneous, although there are also the clusters obviously encoding more than one class, which are the ones that not show any support sample. And then additionally, we computed the inter-class variability of B-Cos similarities across the Pascal VOC dataset. This can give you an idea about which classes have higher diversity within the class or might be similar to specific other classes. For example, you see that on dining tables there are quite often bottles and also chairs around dining tables. Our experiments suggest that inherently interpretable models are not necessarily worse in terms of accuracy compared to black box neural networks. Our results in the FunnyBird benchmark shows that SIC always performs best or very close to the best model in terms of all scores proposed by the framework. In summary, SIC leverages case-based reasoning via aggregation of latent similarity scores. We've just seen that it has performance comparative to black box models. It's quite straightforward to debug, as seen before, via its explanations. It's versatile across backbones and tasks. And finally, we've proved that its reasoning is faithful, which is enabled primarily by the B-Cos transformation. If you're interested to use it, the code is publicly available on GitHub. If you would like to read into it, please visit the paper. And if you would like to reach out for future collaborations, obviously, please don't hesitate to reach out to our group. I would like to thank you and have a great day.